So today we're going to be looking at reactivity of the benzene ring and what happens to the benzene ring when we add substituents and the regiochemistry. Today, I might also introduce a concept of retrosynthesis, where you look at the products and you try to assume how to make it. Now, if you've spoken to this year's third years for chemistry and chemistry with materials, they might have told you how much I love retro. I think for organic chemistry, it is the most important aspect without going into the reactions themselves, knowing where to break, knowing what reactions could possibly work. I love it. Personally, myself, one of my masters is just in retrosynthesis, which means that we might push a little bit here, and then, of course, in your beloved exams. But for another time, donors and acceptor, something that donates electrons will actually activate the ring. If you put more electrons in the electron cloud is going to react more. Is going to react more with the electrophile. So it is donors are activating. Apart from this, they also end up pushing the ortho and para positions. Remember, you only have 3 positions, ortho, meta, para. 3 positions because it's symmetrical. Now, this can be a bit confusing once you have 2 substituents. Okay, so for now, we're just going to speak about ortho, meta, para from the perspective of the main functional group. If you have an electron acceptor, it will be deactivating. Okay, and the electron acceptors could be carbonyls, they could be carboxylic acids, they could be esters. Okay, these are going to be deactivating, with the most deactivating being the nitro group. Now, up till now, you probably have done these reactions as similar reactivity, but they're not. Okay, whenever you change something in chemistry, it's not going to be similar, there are going to be differences. And in fact, for you guys, this is going to be your first lesson. Always look at what's different and understand the why. So, you have the inductive effect. Inductive effect is pushing or pulling of electrons due to electronegativity. You also have hyperconjugation. Now, me personally, do not like to say that hyperconjugation and inductive effects are the same, because they are different. I know that for some students, the methyl group, you say inductive effect. It would be due to hyperconjugation. It's fine, it works, it's a subsection, but it's a complete subsection of its own. Okay? So if you're a donor, you are pushing electrons onto the ring. If you're an acceptor, you are getting more electrons, okay? And you're getting these electrons from the ring. Now, if you push electrons, this is going to be delta minus, and delta minus is going to attract electrophiles. The bigger the delta minus, the more electrophiles it will attract, therefore the more reactive. And for comparison, we will always compare with benzene. Okay, and here you can see that if I don't have the autocorrect function to draw my benzenes for me, they're hopeless. And here we'll have the resonance effects. Now, for benzene, you've been doing resonance effects since 6th form. Use them accordingly so that you can then be able to use these arrows in different groups. If we're going to do something like pyridine, for example, pyridine is going to be the same as benzene. It has a nitrogen instead of a carbon, but it will be the same. So you would be able to use the knowledge that you already have as chemists in your 3rd year or 2nd year. You already have a lot of knowledge in chemistry, and we're going to build upon it. Now, we have to pay attention for the halogens. The halogens actually have lone pairs of electrons. And normally this donation of the lone pairs of electrons onto the ring that will actually activate the ring. But for fluorine, chlorine, bromine, and to a certain extent iodine, they are so deactivating that they will still be ortho and para-directing, but they are deactivating, okay? And they will slow the reaction down. Why? Because even though they will push the charge towards the ring, they're going to be pulling a lot more electrons towards themselves. On the other hand, if you have a double bond, okay, such as carbonyl, then you will be taking the electrons from the ring and normally onto the oxygen. This might sound weird and wrong, especially for the nitro group, where you will have, where you will end up with this kind of structure, where you have three atoms, and all of them are going to be with a charge. In fact, you might remember that normally we don't like charge separation. So this goes against everything we know. But remember that nitrogen can never have more than 8 electrons in its outer shell, due to the fact that it has no d orbitals and therefore cannot use these d orbitals for excitation, which means the nitro itself has to be charged. Okay, sulfur, as in the sulfoxide here, you might get some charge separation as a resonance forms, something like this. And in fact, that is normally how we find sulfoxides. But in this case, okay, it's okay to just draw the double bonds. Mela, let's start with the induction. Induction, they are ortho-para-directing, including benzene, chlorine, fluorine, and iodine that are also going to be deactivating. In fact, what sometimes we used to say, activating para ortho-directing, deactivating meta. No, if they have a lone pair para ortho, deactivating would be, meta would be when you have the double bonds. Methyl would then be an exception due to the hyperconjugation. But for methyl, this is something different and a completely different mechanism. So, I'm not sure if you've done these practicals yet. You might have them in first year or second year. But you will have different amounts of each product. In reality, if you're going by a ratio, you should have, I think it would be 20 on each side. Okay, so the ortho would be 40, the meta would be 40, the para would be 20. But of course, this is not the case, where you will end up having a lot more in the para position, 60%, and less in the other two. In fact, there are two positions on the ortho positions where it can attack. So all being equal, you should see 2:1. 2 for ortho, 1 for para. But due to repulsion, this does not happen. And the conjugation, okay, the resonance forms, they will be able to push the charge onto any carbon that you want, which means that carbon 2 and carbon 4, they are equally possible to be negatively charged. Okay? They are equally possible, to be positively charged. Okay? And they would be stabilized. Now, for for A level, with the resonance forms, we used to normally draw the lone pair of electrons moving before the attack. You can. Here, it's normally better to actually first add the electrophile and then see what happens. Because the electrophile can change a few things. In fact, why would the lone pair want to go onto the benzene ring when the benzene ring is already negative? It doesn't make a lot of sense, but it's because the electrophile is positive and it would induce the change itself. Now, there are three possible structures, three possible positions. So whenever you want to add an electrophile, add it on each position. Whenever you want to add an electrophile, add it on position number 1, 2, and 3, and see what happens. And here we'll see that you're gonna have two structures where the positive charge is gonna be mediated by the methyl group, and one where it won't. And here you will have hyperconjugation. Okay? And here you will have hyperconjugation. But this is not possible on position, the meta position. Now, depending on your group that's already on the ring, for example, here you have the methyl group, you're gonna change your ratio. So the best ratio we've seen until now is the 39:60. If you have something like a tertiary butyl group, which would be that one, that would only give the para position. In fact, here, pay attention, and I beg you to do this. If we're gonna be working some questions, check which groups you want to add, because sometimes some groups will halt the reaction, or else they were directed to a product that you do not want. You then have groups like CF3. Now, CF3 doesn't have any double bonds, and yet it is gonna be meta-directing. So why? Why would this happen? And keep it in mind, because CF3, not sure if we're doing it in this module or not, but it's something you can then easily remove. Okay, CCl3 would be a bit of a problem. So let's see. Always draw the structures. Okay, draw the structures and see what happens. And then take a look, and then take a look, okay, to see what's gonna happen to the positive charge. Now CF3 normally ends up in a position where you are pushing electrons away from it. So this position, the positive charge, is gonna make bigger, less stable, rather than smaller, more stable, and it gives us more chance to react, which means that this is the most stable structure. It's still not stabilized, but it's gonna be the most stable cation, the least destabilized. So here we're not speaking about being the most common, we're saying it's the least destabilized, okay? It's not happy, but it's the happiest.
Sir, you're muted.
I know.
Okay.
So I will re-explain these, okay? I will re-explain these. Are you all okay at home?
Yes.
Yes.
Okay. Listen, that's why let me try and do it as you used to do it for A level. Okay? We see the differences and we see the similarities. Okay? I would highly recommend. You might have done these at A level, but I truly recommend that you try and do these from the scratch. Okay? Because that normally gives you a much better indication. But for A level, you used to do this. Now, my aim was to try and finish 10 minutes early to give you a bit of a break. I'm not sure that today it will be possible, okay? Because we did start a little bit late. But normally, I will try and do that ħalli kulħadd ikun content. So, at A level, let's say you had phenol. Okay? So at A level, you used to do this. Push the electrons from the phenol and move the electrons around. Okay? So you used to call it inductive effect or mesomeric effect. Now, in reality, I would rather that you work them as we are doing now. Let's say you have the phenol anyway. So you used to have 4 structures, right? 4 structures. Okay? And you have the electrons moving around, which is fine. It's fair enough. That's what you have done in the past. But the structure doesn't really exist. It's the electrophile attacking that is more stable. Okay? So I would prefer if you do it that way. So here, and this will make life easier for you later on as well. So here, it's not about whether this is inductive, positive, or negative, or mesomeric effect. Okay? Here, you have the structures being more or less stable than each other. So if you have these 3 structures, which 2 are going to be most stable? The ones where the methyl group is going to be adjacent to the positive charge. So it's these 2. The other one, the stabilization, is a little bit less. It's still more stable than benzene, but it can't hyperconjugate. Okay? And when you have a structure like this, even though these 3 structures, 1, 2, and 3, are all going to be present, it's the third one that's going to be most present. So I would be a little bit careful and skeptical in using the mesomeric effect and the inductive effect here. They are a result, okay, but now you're going into a little bit more detail. Resonance. Okay, so up till now, we've spoken about induction effect. Okay, now we're going to speak about the resonance forms, which would be the mesomeric effect. So for the CF3 pushes electrons into the ring, right? So if it's going to push electrons, this positive charge is going to be bigger now. And there, sorry, it's pulling electrons, not pushing. It's pulling electrons towards it. But I always call it push. But now, if it's bigger, it's less stable.
Okay.
If it's less stable, it will not react in that position. Okay? So let's say we have resonance forms. And we have a similar situation. Okay, you want to add the nitro group. Okay, you have an amide, and you want to see what's going to happen. The numbers here correspond exactly to what we said before, where ortho and para, with para being a lot more abundant. Again, add the electrophile, and add the electrophile on different positions, on 1, 2, and 3. Now, these positions, I'm calling them 1, 2, and 3. You can call them whatever you want. Okay, A, B, C, alpha, beta, gamma, whatever. I don't care. It's for you to know that you are actually putting the electrophile on all the required positions. And at that point, see what product you've got. And you will have these 3 products here. Okay? Once you have all the 3 products, then draw the resonance forms for each individual item. Once you have the resonance forms, then analyze those resonance forms to see which one is going to be more stable. And in fact, here you have 2 of the resonance forms where you have an octet of electrons. And you know, I think it's one of the first, either first week or second week of organic chemistry 1, where we say in resonance forms, whenever you have an octet of electrons, it wins over everything else. It's going to be the most stable. Okay? And therefore, that is what happens here. It wins, is the most stable, therefore, it's going to be the one that is most abundant. Apart from this, now, this is not always the case. So I'm making a disclaimer here. But the more resonance forms you normally have, the more stable you will be. So 4 against 3 against 4. But then again, always look for the octet of electrons. If you have 1 resonance form and it forms an octet, it's more stable than something with 5 resonance forms without an octet. Remember, you have the major and minor product, so on and so forth. This would be the major here. Okay? Now, you can have acceptors. Acceptors are going to be with a double bond. Okay? So again, let's see what happens. Add the electrophile onto each position. And you're gonna have these 3 structures over here. Always starting with the same thing. Always starting with the same item. Once you add the electrophile onto each position, then see the resonance forms. Okay? And the resonance forms will clearly show which one is going to be the most stable. Now, this is why I told you before, pay attention with the numbers. It is a good indication, but here it won't work. Look at this resonance form and this resonance form. You have 2 positive charges adjacent to each other. Okay? They will repel. They will repel. On the other hand, all these 3 are stable. I'm making the air brackets, or whatever you call them nowadays, because they are actually not as stable as benzene, but they are more stable than having 2 positive charges. Okay? Imagine if you have Philippa and someone else fighting for the same guy. If they sit next to each other, they will fight. There's still tension in the classroom if they're both in the classroom, but being close to each other, they will fight. Okay? Now, I hope it never happened to you here. Now, because it creates drama. I've seen it in 6 forms. Not good. Now, Pay attention, okay? Now, you might tell me, but it's only 1 out of 4 where you have the repulsion. But remember, in a resonance form, to go from one to the other, you have to go through this state. You cannot just avoid it. And anytime you go to that state, it's gonna be destabilized. It's not going to be happy. It will immediately lose the proton. Okay? It will not want to have the two positive charges next to each other. Fuq ġaj istiġġieldu żgur. The exceptions. Of course, there are exceptions. Okay? Halogens. Okay? If you have bromine, okay, if you have bromine, you have deactivation, but it's still ortho-para directing. You have deactivation, but it's still ortho-para directing. And since bromines are huge, the para will win. The para will take over. So let's see. Again, attack the same position, all of them, and get the 3 products. Once you get your products, then see what you're gonna get. And in fact, in the ortho and para attack, you'll end up having a full octet, which is more stable, which means that you're gonna get a situation where you are going to have a stable conformation that is slightly overall deactivated. Okay? Now, this is a quick summary. I think some of you might want to copy them. I sent you the PowerPoint. It's on Volhard. Okay? But have an idea. I'm not expecting you to know all of these by heart with their values, so on and so forth. But I do expect that you know what an activator is, the activator, ortho-directing, para-directing, meta-directing. I would want you to know, more or less, that nitrogen-containing compounds are more reactive than oxygen-containing compounds. Substitutions on the nitrogen group decrease the reactivity. Amide is less reactive than the amine, because there you might have some resonance forms in the amide itself. The lone pair might not be fully available to interact with the benzene ring. It might interact with the carbonyl. So please know these things. Again, not necessarily expecting you to know everything inside out. Now, for the meta directors, the strongest deactivating doesn't have a double bond. It is a tertiary amine. The strongest deactivating group is the tertiary amine. So please keep it in mind, as it is important to note. Okay? And what happens here is a situation where the double bonds in the ring can actually go on and stabilize the positive charge on the nitrogen. Now, any questions? Any questions from home?
None so far.
You're perfect. No. For a second, I forgot you're not the first years. And I was gonna call out on some students who normally always ask questions. Whatever the lesson, they will ask a question. Normally, the class rep who does that. But for you guys, I would accept Giles to be the victim, the lamb of sacrifice. Now, what happens if you have two substituents. Who would win? And this is a fight where one of them has to win. Now, in some cases, you might be lucky that they will be pointing to the same position. In others, they might not. If they are not, and you have an activating or deactivating group, then you know which one is going to win, the activating. But if they're both activating, then you use a stable. Okay? So, let's say the most powerful activator controls the position of attack. So normally this would be either a nitrogen containing group. If there's no nitrogen containing group, it will be the oxygen. If there's no oxygen, it will be the methyl. If there is no methyl, then we have to look at which one is the least deactivating. If you have, there are three classes of substituents, as I just told you, amines and phenols, halogens and alkyls, and emitter directors. Again, just have an idea. You've already written the list. Now, I'm not going to be a bitch and give you two groups that are very similar in reactivity and expect you to know what these are going to be. I forgot this is going to go on YouTube. But it's important to have an idea. If there's competition, the outcome might be difficult to predict. But then again, if you have a group like this and like that, the highest probability will be this position over here due to repulsion. Okay? Ethyl group is bigger than the methyl. But it's difficult to predict. I don't expect to have 90% and 10%. It will probably be 60-40 or maybe 70-30 if the group is huge. Now, for the first one, it does not matter. It's perfectly symmetrical. As long as you only have one substitution, it doesn't matter. But for these two, it does. Because the ortho and the para positions, again, let's call them A and B. They are going to be very, very different. They are going to be very, very different. Okay? And most of the time, this will be around 50-50. Again, position B is more stable than position A because it's a bit freer. But it's not gonna be too much difference. I didn't try the others because those are still A and B there from the other side. And in sometimes you can be lucky and have something like this, where you think they are both pointing to the same direction. That would be highly unreactive. You don't just have one substituent that is deactivating, you have two. Normally, nitro groups, to actually react them, you need high temperatures. So if we're going to go and say, okay, I'm going to have two deactivating groups, then prepare a pressure cooker because you need high pressures, high temperatures, and your product might still be in low yields. Guideline 3, look at the bulkiness of the groups. Okay? I've already spoken about this a little bit, but you need to find the position that is less sterically hindered. And guideline 4, the strongest activator always wins. So here you have these two positions. But then, because you have the bulk in S, it will of course prefer the position on the left. This is a good note. I don't agree that life gets easier, because if you have more substituents in an exam such as mine, that means you have to put in more substituents and you have to know what order to use. But that's something for another day. Okay, but higher substitution positions, that means you only have a fewer other possibilities. You will have few possibilities, which means that at the end of the day, you're gonna be in a position where there is only one viable place. Now, I'm not going to do strategies today. Okay, I would like to stop this lecture here, unless there are any questions. So, any questions? Okay.
So
Yes.
you will be uploading these on the VLE?
At some point in my life, yes.
All right, thank you.